Bismillahirrahmanirrahim. Bismillahirrahmanirrahim and Assalamu alaikum. Before I begin with the session, I'm truly grateful to all my participants who have waited patiently to begin with the session and the true gesture of attending this webinar. I welcome here Mr. Muhammad Ahmed Mustafa, who agreed to deliver this webinar on a very short time span. Thank you, sir. Thank you for so cooperative. Okay, before I begin, a brief introduction of Sir Muhammad Ahmed Mustafa. Today we have a topic from his side on glacial melting from the eye of fluid mechanic experimentalist. And about Sir Ahmed Mustafa, he's working as senior engineer in water agriculture division. And he's on his doctorate degree at Georgia Institute of Technology, Atlanta, as Fulbright scholar from Pakistan, from School of Civil and Environmental Engineering as Professor James Tin Shong Wang Fellow. He has been a part of cultural exchange program at Portland while representing Pakistan. And about Sir Ahmed technical expertise, he has practiced consulting engineering in the field of hydraulic structures, irrigation distribution, and at NESPARC, which includes Trimu and Panjanath Barrage rehabilitation and PIR. His interest revolves around the hydraulics, particularly within the experimental domain. And other than this, he has been extensively involved in building an optimized, controlled facility for generation of homogeneous and isotropic turbulence through random educated synthetic jet arrays while incorporating fractal shaped nozzle for jets. And he has his massive research on the focus area is on the quantification of ice termini melting under the influence of subglacial plumes in Arctic conditions through novel experimental methods. Sir, I welcome you here, and that's been very, very generous of you. Now, I request you to please proceed with the session. Thank you, sir.
Okay, thank you so very much, everyone, for having me. Well, Sabika has said a lot about me, but I guess that's quite a lot, which I don't really deserve, but still. Yes, that's true. I have been notified on a very short notice, and I'll try to do justice as possible as I could with respect to the presentation. However, I would like to make this presentation, this session, as interactive as possible, because I can see in the chat room there are a lot of young engineers who could really step up and get a higher education, and I would be very much happy to help them in every manner. About myself, as you know, I've been working in NESPARC for the last 6 years, and then I took a leave, and then as she mentioned that I went on to Fulbright scholarship, which is quite a life-changing experience. And then I went on to continue my PhD after completing my master's and so on and on. But I would highly recommend everyone for sure to have an exposure, especially foreign exposure, which includes US particularly. Today's topic, it's more like what I have been doing so far, what I did in where I will be keeping the presentation and what I did in master's, which was quite a small project. And it was just about optimization of homogeneous isotropic turbulent tank, how we used fractal geometry, how we used the latest technology incorporating into the civil engineering domain and utilizing those technologies to enhance the sorry? I guess it was just a glitch. So as I was saying, what we did in the homogeneous isotropic tank is we introduced the latest technology, coupled it up with the civil engineering application, which particularly served the research part of the engineering instead of the application. However, one can argue that engineering application is nothing but the application of whatsoever the fundamental sciences is. So fundamental sciences are much more important. Yes, I agree. Without further ado, the first, what experience I had. So I have been, I was at the Glacial Model High Secondary School as well as LGS. Then I did my undergraduate from NAST, and I served NASPAC for the past 6 years in many different divisions before I found my final calling. Then I went on to a cultural exchange program, which was in Portland State University, Oregon, USA. Keeping up on with the pace, I moved on to Georgia Institute of Technology as a Fulbright scholar for a master's student. I did my master's as a hydraulics and water resource engineer, and did a couple of research problems. While doing the research problem, research really intrigued my interest, and thanks to the funding agencies as well, who funded my PhD program to pursue my passion for the research. So as I mentioned earlier, I will be starting with the random jet stirred homogeneous isotropic turbulent tank. It is, before I start, let me tell everyone, so I would request Sabika if she can unmute everyone so that they can mute themselves. And whenever they want to ask a question, even during the presentation, they are more than welcome to ask any question.
Actually, the reason of muting all the participants is basically the background interruptions that we often hear before this during the session. So that is the reason we have to mute the participants. But I request all of you either to drop your queries on the chat box, or the raise hand option is also available to them. The raise hand option is also available. Thank you, sir.
Now I get it. I know I get it now. So yeah, for sure. If you ask a question with respect to the research I have, with respect to the experience I have, or any other question which you want to ask, even if you want to ask me about the life in the US, I would be much more happy to help you. So mostly, I've been working with the turbulence, and if you're asking about any person about the turbulence, turbulence is nothing but, I would say, it's a chaotic process which cannot be determined deterministically, but statistically. So it's actually a phenomenon through which any pollutant or any substance is being transported from one place to another place. How the turbulence is playing a part in the water resources? Yes, the mean velocity has its fluctuations. Every mean velocity has its fluctuation, and those fluctuating velocities creates eddies, vortices, so many things which have many times have heard. And these are the transport agencies which transport the pollutants or diffuse the things around. I wouldn't be going into that. That slide was just an introduction of whatsoever the turbulence one can perceive and how it can be defined, but there are many definitions without any argument. My work with the turbulence is always with the phenomena of transport of environmental fluids. This is a slide in which I have shown you how the different transport processes occur and how different types of turbulence-induced mechanisms are happening, like bottom shear, buoyant convection, wind shear, through which the oxygen is being regulated in the water, and how the oxygen or other pollutants, just like nitrogen or potassium or whatsoever the things are in the water, are being transported through the soil or through the air in different means. What are random jet stirred tanks. So in the research field, I guess I hope many of you already knew about it. The mean velocities are really interacting with your turbulence fluctuations. It's very difficult to actually decompose the velocities into mean velocities and the fluctuating properties. So what we really do in research is we try to isolate the random or the turbulence u prime, v prime, w prime fluctuations in an isolation, and then we try to study how they behave, and then we try to predict statistically, not exactly, how they are being transported and what will be their role in different mechanisms. Over here, you can see there's a random jet synthetic array. It's an array, you may say it's a grid, in which there are different jets. These jets are nothing but a very simple phenomenon, simple submersible pumps. However, these are being connected to a program, to a MATLAB or the Arduino. You program it on the MATLAB, you make these jet on and off randomly, and then try to find the vortices or the turbulence in a specific field. But the characteristic of that turbulence needs to be homogeneous and isotropic. What is homogeneous? Homogeneous is nothing but the intensity of the turbulence, which is the U prime, their production, is same in every direction. What is temporal is means that they are same throughout this time. What does it mean? It means that we don't really have to look, you cannot draw a conclusion of any study within just an instance. So what you really need is you need to study those things over a long span of time and in every direction. That's why we need homogeneous isotropic turbulence, that it should be same in every direction and it should be continuous with respect to the time. This is another example of whatsoever the orientation which we created with the homogeneous isotropic turbulence. And this is just, it was introduced by Ivan Variano, and they have different dimensions there. Now it's actually quite an old technology. They have different dimensions with respect to tanks. This study can be, these homogeneous isotropic tank can be used in different studies, which includes erosion, which includes pollutants being mixed, which includes plumes, jets, and many things. This is just for an overview. If someone is interested, I can share the slides. This is a comparison between different scientists, different engineers who have been trying to build a homogeneous isotropic tank. And they have been trying really hard to achieve a high Reynolds number. We know that the high Reynolds number is a key in natural phenomena. In laboratory, you have always been trying to achieve high Reynolds number, but it's hardly feasible, especially when the turbulence involved. Turbulence Reynolds number is a Taylor Reynolds number. If you must have been in, if you're interested in fluid mechanics, it's another topic. But what I'm trying to say is that turbulence has different scales with respect to the length. If I have to be very precise or very understanding, it's more like you see the sizes of vortices, different sizes of vortices in natural flows. Even in the rivers, there are big vortices and then you see the small vortices, and those vortices has lengths, and those lengths are the Taylor lengths, and from those lengths you can actually get the Reynolds Taylor. So in the lab, we have always been trying to achieve a higher Reynolds number by increasing velocity, and then there's been a conundrum that how to achieve the Reynolds number without introducing any mean flow, because mean flow is actually the one which is introducing or injecting the energy into the system. So the maximum Reynolds number, Taylor Reynolds number with so far has been achieved was 372, 378, which is still low as compared to the natural processes of the environment. So what we did is, before I move on, let me just give you a quick how the random jets look like. When I say random means they just pop up without any pattern. It is actually a pattern, but it is a Gaussian pattern, a Gaussian curve, which is the most occurrent statistical process in the atmosphere or in the environment. So just assume that these blocks, each block is representing a jet, a submersible pump, and it has a nozzle, and it needs to be randomly switched on and off. And it needs to be designed with MATLAB, which is, I guess now it's easy for, it's actually 100 seconds, but on the very fastest with 1 to 20th. It keeps on, off, on, off, on, off. And both the on and off are being distributed randomly over the Gaussian distribution. So each jet you see is on for 3 seconds and off for like 30 seconds. And then we want to see whether they are interrelated. You must be asking that there is a possibility that maybe one synthetic jet is actually correlated to the other one. And then if they are, that means they are actually trying to create a mean flow that is in a single direction. But for that, let's again check the correlations. So these two curves are showing that each and every jet is not correlated to any other jet except for its own. That's why you see a diagonal correlation of 1. Beside that, there's almost equal to none. Moving on, how do we increase the optimization of synthetic jet arrays? Fractals, these are very interesting. Actually, this was the most interesting topic I came across. Was in fractals, there hasn't been any formal mathematical definitions. Mandelbrot, who actually invented the fractals, and you will be surprised how the fractals were invented. So the Disney, they have their own graphics, they have their own mathematicians, and they have been always working to improve the resolution and the outlook of the cartoons and trying to make it as real as possible. One of the biggest questions for them was that there is a certain limitation to the shape. If there is a triangle, it's a triangle. And when we zoom in, it's a triangle. And let's say if you are making a mountain, and you just represent it as a triangle. But as you zoom into the character, which is zooming in the mountain as well, you don't see the mountain. You just see a flat line, which is not actually like the reality. So what they did is they introduced Mandelbrot fractals. So fractal itself that they keep on repeating themselves at every dimension. It can be defined with the 3 things, which is self-similarity. As you can see that this is actually Kuh's diagram. And this Kuh's diagram is nothing but repetition of itself. This is the first iteration, second iteration, third, and so on. Secondly, the fractal dimensions. We have always been dealing with 3 physical dimensions, that there are 3 physical dimensions. And if you want to include the 4th one, which is obviously a time, but it's again not a spatial one, but a temporal one. So in the physical space, we have 3 dimensions. But for the fractals, interestingly, they have non-integers fractals. How they are introduced, how they are being calculated, that's another topic which I'm gonna put on to you right now. But if you are interested, you can for sure look up on the internet. And if you are so interested, you can ask me questions. And then they are nowhere differential. Either they are discontinent, which is again non-differentiable. Either they are straight, which is a constant, but they are non-different. If you can generate any shape, and any shape can be described with respect to the algebraic equations, x squared plus y squared divided by a is equal to r. This is another thing for the circle, just an example. Same thing can be done with the fractals. But if you can devise an equation, and then in an Euclidean space, if the dimension of that space comes out to be non-integer, that means it's actually a fractal. Congratulations, you just found a new fractal. So this is just again me describing about whatsoever the final aim for improvement in homogeneous isotropic turbulence is by using fractal geometry. What we did, we just used two kind of fractals. The first one is the fractal opening. The fractal opening, which you can see even in this diagram, there is opening. Only the boundary condition is different, but not the inside of the fractal. There's no hurdle. We used Hooch curve, we used Minkowski island with a fractal dimension of 1.26 and 1.38. Sorry. And then we moved on to a fractal grid. So you have seen a regular grid, which is just a mesh. But now I'm going to show you how the fractal grid looks. Before moving on to fractal grid, these are the two Minkowski and Hooch diagrams, which is in front of you. We decided to went on to the fourth iteration. These are the cross-sectional areas and different major minor details with respect to the figures, which I know you will not be interested, but just mention how we compared apple to apple, keeping the cross-sectional area same and all those things as possible as we could. Moving on to the fractal grid squares. So this is a grid scale, which interestingly I designed as per the fourth iteration. And this, the cross section which you are seeing is the cross section of the nozzle through which the water is. The big rectangle with a thick lining is the first iteration. And if you look at my mouse, if you could look at my mouse, I don't know if anyone can confirm, but I assume you can see that. So this is the second iteration. And then this is the third, and this is the fourth. And the thickness is of each sphere thickness. What is the thickness? And this is in millimeters. You must be asking, it's quite thin, how you would be able to manufacture it. And interestingly, I'll show you how we manufacture it. This is actually the 3D diagram of the fractal grid, which I built. And you can see it's an opening. One must be asking how you can assume that there will be, the flow will be developed. Well, if you can see, it's quite long along the flow line. So that would be another aspect which we just considered and give a transition of 1/6 at the start and then give 6D for the development length. And that's how it forced out a jet. Similarly, this is the Hooch triangle, which is an opening. So forth, we used a 3D printer to print these fractal muscles. At the Georgia Tech, it's one of the, I would say I was fortunate enough to work in the invention studio where you can work or print any 3D print or laser cut or do anything which you want to. So what I did is I just 3D printed it. The next thing which we wanted to do was to put it in front of the nozzle and then study how the homogeneous isotropic turbulence can be enhanced. But thanks to the code, we could not perform the actual experimentation due to the code. However, this is another paper which later on showed up the simulation. They haven't been up to the fourth iteration, but they have only been to the third iteration, and they have shown that yes, these fractal grids can actually enhance the turbulence, homogeneous isotropic turbulence. But still, there is a lot of room to do the research, and we are surely looking forward to do this project again. Now, shifting on to the gears, I will be moving on to my PhD PhD topic, which is the prime most important for me right now. Before I move on, I just want to again reiterate that as a fluid mechanics, what we build is we build the predictive models for heat mass transport. And if you can see the Navier-Stokes equation, which is the conservation of fluid momentum, it has nothing but the velocities and the concentration. If you could look, if you can see, if you could find the velocities and the concentration, in a sense, if you could find the vector and the scalar field of a fluid, it will be very easy for you to dwell on to what the fluid flow is actually doing and how each and every mass transfer, each and every pollutant is being transferred. There are a few of the simulations which, as a PhD student, or you may say the graduate research assistant, I did with Dr. Chris Lai, my advisor. And this is just a video showing how we actually incorporated different shape of the jets and plumes in order to treat the seawater at the shore of Hong Kong. This project was funded by the Chinese government, and at Hong Kong is quite densely populated. They don't have any land contact, they all are sea, and they are all surrounded by the sea, and whatsoever the sewage is, it is being treated and then discharged into the seawater. However, that sea water is again recycled back to the shores, which is actually detrimental to the beach and to the public health, for which we introduced different geometry of jet nozzles at far field in order to mitigate the detrimental effect of the discharge. Well, that was the simulation. However, the simulation needs to be validated through the experimental. And this is one of the experiments we did at Georgia Tech, in which we have, we call it fractal plumes, through which different heights and different geometry of the jets nozzles are being introduced in order to enhance the mixing efficiency. Okay, I think I have already described this before moving on, that the turbulence itself is nothing but the fluctuations, and how the fluctuations that can be visualized are nothing but the vortices. And these vortices moves the heavy metals, organic solvents, or different things, any pollutants, which is the C prime, which is the scalar quantity. Similarly, if we see the heat is actually also a scalar quantity. One can argue that it has a direction moving from high to low concentration. Yes, it does, but that is a diffusion process. That's how the heat is being transported from advection fluxes through UCPAM. However, this is the phenomena which if we looking beyond the micro scale, but if we go to the micro scale or low, which is the molecular scale, every phenomena with respect to even the concentration or the velocities, they tend to follow the diffusion equation, which can be seen at the bottom, which are nothing but the fluxes. So again, reiterating, if you know the velocities and if you know the scalar quantities, then you can actually dwell or research on any fluid flow. What are the jets and plumes? Jets is anything which is coming out of a specific certain geometrical nozzle. That is a jet. If the momentum is conserved, till then, conserved, and it's dominant, then it's jet. If the momentum is not dominant and the buoyancy has taken up, it's called plumes. You see many plumes in your daily life, just like few of the examples is fire plumes, exhaust plumes. Even the COVID studies are being done as jets and plumes, because whenever one is sneezing or coughing, it's nothing but jet or plume. Then there is another application with respect to the oil spill, and this is actually a picture from Gulf oil spill. If someone can go back into top of the there was a U.S. oil spill. These examples are just to introduce you what are the jets. Now the question comes in how the jet and plumes are being introduced in the ice melting. We will discuss upon later, but before I go on, I emphasize that we need to find the jets. We just need to find the velocities and the concentration. Now, being an experimentalist, we need some tools how the velocities and the scalar quantities are being measured. Well, one can argue that you can just insert the parameter and then just find the length of the speed of the propellers. Yes, that's what we have been doing so far in Honeypot, but now the science has enhanced and we are looking into the very micro scales. So what we use is particle image velocimetry. Is you can see there's two pictures, picture 1 and picture 2. They are the picture of vortices at two instances. The first one is t, and the second one is, let's say, t plus delta t. If I redo it on the animation, you see something is moving. So it's actually a vortex. Once you have these two pictures, you have the delta t, you have the two pictures, you have the dots. These are what we call, these are the seeding particles, but you can also call it a noise in the picture. These two pictures are correlated and moved upon, just like, let's say we overlap each other, but they don't really overlap exactly. Then I move the picture 2 in every direction and finally find one good spot where they correlate or be cross correlation. And now we know that in which direction I have changed the picture to. I know my magnifications, you may say the scaling. Now I know the direction. So through this, I can easily get my vector velocities. By just correlating these two pictures, what I get is I find my vector velocities. On the x-axis, you see the x pixels, on the y-axis, you see the y pixels. And you can see over here in the animation that it was a vortex, and it in the figure, I can see the velocity vectors at each resolution. But then you say we can go further refine it. Yes, we can further refine it if you decrease the magnification or you increase the particle intensity. You further can resolute your vector velocities to the smallest magnification length of your canvas. So this is the thing which we did with the particle image velocimetry. That means we have been, let's say, we have been able, not saying, rather we have been pretty much good with respect to x, y, 2D planar velocities through this PI. The other thing is that it is the scalar. So this is quite novel thing which we have been doing recently is the laser induced fluorescence. What we do is we put two dyes and each dye has a reflection. So at different wavelengths. So let's say if I fluorescence the two rhodamine B dye, and then there's another which is sulfate rhodamine 1 dye. They absorb almost the same wavelength. 535, 550 is not much of a difference. But then made at different wavelengths. What does it mean is that I shine them at the same light intensity, but what they do is they emit back at different wavelengths. So if I put some filters let me make it easy for you. It's not correct, but it's just an analogy that if I shine these two dye with a green light and put the filters, I can see that the one will emit the red light and the other one will emit the green light. I know it's not correct, but it's just an analogy how we used and manipulate the filters, the long pass and the short pass filters, to get two different dyes in two different colors. Well, once we have done that, we are able to see the two different dyes. We can see that both of the dyes are shown with the same light. And once they are done, one of the dye is actually sensitive to the temperature. So let's say this is the red one, this is the green one. we have captured both of the lights, but one dye is not sensitive to the temperature. The dotted line you see is at 40 degrees Celsius, and the solid line you see is at the 20. So there isn't much of a difference with respect to the intensity, or you may say the brightness of the fluorescence. But at the same time, with the rhodamine dye, the intensity varies a lot by a factor of 10. This needs to be captured. One can argue why we need the second dye. The second dye is needed to normalize all the different correction factors in the first dye, which includes the laser attenuation, it includes white field balancing, it includes the attenuation of the laser. So as the two dyes, two cameras, this is the first dye, which is the rhodamine B dye. This is the second dye. I don't know, you will be able to see it on a small screen, but if you get onto the big screen, it will be pretty much clear that on the first image, you see a very bright dye. And even with this brightness, there is a difference in intensity at different pixels. You do all these corrections, and as soon as you do all these corrections, you get this image, very beautiful. So what this image is describing is actually a jet which is placed at the top, shooting the jet downstream. The jet is at the temperature 0 degrees, and the ambient water is at normal room temperature, which is 24, 22. And you can see the jet is being thrown downward, and it's expanding at the degree of 6 degrees, which is the characteristic of jet. And you see the different vortices phenomena, the vortices, the velocity variations, the concentration variation. Now, through this color scheming, you can see that over here, the temperature is quite near 4 degrees Celsius, whereas the ambient temperature is 22. Now you know the scalar field as well.
I request my participants to please stay connected because of this sudden electricity issue. Our resource person is still here, and he'll be resuming the session right after this resolving of this electricity. Thank you.
जी फिर आवाज गुम हो गई आवाज नहीं आ रही
Can everyone listen? Hear? Miss Sabika, अब आपको आवाज सही आ रही है?
We can't hear your voice, and the mic is already unmuted.
Interesting. अब आपको आवाज आ रही है मेरी?
ठीक है
I think there is some voice. Voice is not coming.
कथा हो गया मैं लिखते ही कोई नहीं ऐसा क्यों इनमें सही नहीं है
आप लोगों को मेरी आवाज आ रही है? Are we good to go now?
नंबर नाम मोहम्मद इजाज तनवीर
Sir, I think now the voice is clear to our participants. Please.
Okay.
Thank you.
Sounds good. So I know I have already taken quite a lot of time, so I will be quick as quick as possible. Um, yeah. So in the summer, we have lakes. I guess Sayyid Ali Hassan is his mic is on. Okay, so in summers we know there's rainfall, and then there are lakes which are on the surface of the Arctic, but somehow they are actually connected to the bottom where the water goes on. So they go on to the bottom, but if they are going at the bottom because of the gravity, where they are heading. So what we can find is that with the new satellite imageries, we can see that these lines you see, these are the subglacial channels. They were the old channels which were being eroded or made by the subglacial water. So whatsoever the lake is, so once the lake is being formed at the Arctic surface, that lake is connected through the subglacial channels to the bottom or the surface of the earth underneath the glacier, and they actually erode and make their way towards the sea. How these are being confirmed? These are being actually confirmed by these images. So you see that my mouse is pointing at an image which is of the Arctic, and you see the pink color which is showing the temperature of the far field sea temperature. We see there's a lot of melting, as there's a red color over here, which is which is showing that due to the ocean circulation and the hot water intrusion, there's quite a lot of melting occurring over here. But why the melting is observed over here when it is actually being surrounded with the cold water, which can be seen that this is blue. So this melting is actually being exacerbated or enhanced due to the underneath glacial plumes. So in this image, you can see that there is a surface. The surface leg is connected to the bottom channel. The bottom channel run along the termini of the glacier, and then it rises up. Why it rises up? Because this is a fresh water. This is seawater. Seawater has salinity, which is always denser than the fresh water. So first thing. The other thing is the fresh water is being melted at a temperature of 0 degrees Celsius, whereas the seawater, we have learned through the science that it is at the temperature of 4 degrees Celsius. And at 4 degrees Celsius, and a lot of salinity, seawater will always be denser than the fresh water. So it rises up. As it rises up, the plumes has its own characteristic that it entrains the ambient fluid, this air, which can be seen over here, which further introduce the hot water. This hot water is being introduced, and the boundary condition at the termini of the ice keeps on recirculating and melting. Well, this is one of the particular phenomena which I am working on, and we have observed through the different studies that there are many factors which actually contribute into the different melting rates. Why this melting rate is important? Because in one of the most recognized melting model or the melting simulation right now is MITGN, which is from MIT University, and it's an open source software. Even in that, we haven't seen any strong model for plume melting. It's just a speculation over the years, the experience they have shared, the readings they have taken at the sites, and being randomly incorporated into the model. But again, if we are comparing the Antarctic and Arctic, the factors or the model parameters are quite a lot of different. That means that the fundamental science is missing. So what are the fundamental sciences? Now, when you are going for a challenge in fundamental sciences, you need to isolate one single problem, come up with a model, and then apply it to the person. So what we observed is that why they are different, they could be different due to the plume configuration, like geometry. Either they are the singular jet, or they are a line jet, or they are a spatial jet, or the ocean density stratification. Ocean density stratification is different at Arctic and Antarctic, and then the slope of the ice face. You must have seen that there are scallops at the ice face, and due to those scalloping at the termini of the glaciers, they have different slopes, and due to that different slopes, the melting rate could be different. Roughness of ice is one of the very detrimental, or you may say one of the key important factor which is contributing in quantifying the melting of the ice. The studies have shown that even the aspect ratio of the glacial melting is aspect ratio of the glacier is contributing to different melting rate of ice. I'm going to address these few things, and then you can decide how important it is. So, with these things known, we know the salinity stratification, we know the temperature stratification, atmospheric density stratification, and all the parameters known. We now only need the velocities and the scalar quantities like heat and momentum transfer in order to find the basic or come up with a basic model. This is one of the models which we have been using so far. It's called the Jenkins model, in which there are actually three state equations in which you find the temperature, you find the heat fluxes, and then the salt fluxes, and through these models you come up with the melting rate, which have been used so far. STT is the Stanton number with respect to temperature. STS is Stanton number with respect to the salinity. However, both of them are quite in stark contrast from if we compare it with Arctic and Antarctic. That means there's quite a lot of room in model improvement. The next thing is we come up with we wanted to first go for the baseline models, and through the baseline model you have to come up with experimentation technique. And for the experimentation, we did one of the simulation. It is only singular simulation of ice melting without any background flow, without any jet influence in ANSYS, and wanted to see how the mass fraction ratio changes with respect to the geometry. This is the length of 33 centimeter, and we assumed, and referring to back to the literature, we came up with a solution that let's do it 3 times, and the jet will further enhance, wall-bound jet will further enhance the mixing, and it will give me a window of 10 minutes to observe the experimentation. After coming up with the solidification melting analysis at ANSYS, we did a SolidWorks drawing. It's another software. I highly recommend one, especially the engineers, to learn it, because it also helps in analyzing BOQ drawings, construction drawings, all in all. So this is actually a tank. It's representing, this is a slab. These dowels which you see will hold the ice with respect attached to them. Once it's inserted, a jet plume is being attached at the bottom, which will be offshooting at the face of the ice, and it will be melting the ice. Question why this is so long? This is so long because so that the far field condition cannot be changed as you see in the ocean, and only changes which are happening is at the near field. This is how we make the ice, and I'm going to cover it now because I know you people are covering quite a lot of work. So this is the experimental setup which I built. Now, one of the best, I would say, experience was in Georgia Tech especially, is that you get the chance to do everything by yourself, even the welding or joining or even construction is 80-20 aluminum frames. So whatsoever you are watching in this picture is being built by me. So this is the tank. You see the 2 cameras. You see 2 cameras for PIV. You see the 2 cameras for LIF. These are the 2 cameras which simultaneously capture the velocity as well as the laser induced fluorescence scalar quantities. Moving on to on the right side, you see this is the ice which we mimic as the glacial ice. And at the bottom, there is a jet. And from the bottom, we shine the laser through the optomechanics to make a sheet, which is illuminated high enough. One of your questions should be why we use laser, so high intensity laser. And the answer is that because the flow field are so fast, you need to capture at a very small instant. And as you decrease the exposure time, camera needs a lot of, or you can say the sensor, camera sensors, CCD sensors, need a lot of bright light to capture the signals. Moving on to that, this is the final thing which we did at the Georgia Tech lab. So this is an image which you can see is showing the temperature variation as well as the velocity fields. So we see that there is a wall-bound jet. The velocities are at the wall of the ice wall. On your left side there will be ice wall and not represented in red. The velocities are almost equal to 0, and then there is a peak region where the velocities are quite high, and then the velocity decreases again due to the image. And then the other thing which you see is there are slanting arrows. These slanting arrows shows how the far field hot temperature water is being entrained into the jet and being transported at the face of the ice to enhance the melting. These are the few of the details which we did with the experimentation, 2.71, 25 hertz camera magnification of 0.35, and I say magnification of 0.35 means at the denominator it will be the real length, and at the numerator it will be the length of the sensors. These are the velocity fields, velocity vectors, just to show you how the velocity fields look like. These are the baseline results for whatever we have been doing. These are the velocity fluctuations, URMS. This is the mean velocity, U, mean velocity Y. U and Y are in the same direction as being represented with X and Y. Moving on to different lengths, it was being measured at 80D. That means 80D from 80 dia of the jet, and then 150 is 150 times dia of jet away from the face of jet. This will be the velocity profile. These are being normalized by Vmax and the width of the jet, which is showing the self-similarity, and that is one of the characteristics of the jet. The 0 is at the wall of the ice, and at the wall of the ice, ideally, it should be 0, as per the Navier-Stokes equation, all the boundary there theory. And away from the boundary, you have this molecular diffusion. That's where we cannot really capture over here, but we do capture the molecular diffusivity over here. We have the readings over here, and then you see the mean flow states. Moving on, these are just the results, and it will be obviously shows that these jets are even the 3D jet is more comparable to having an independent entity, but sometimes they show themselves as 2D wall jet instead of 3D wall jet. 2D wall jet or line jet, they are the same thing. Over here we see the 3D jet, but these results are actually with respect to the fixed wall. Interestingly, first we started with a fixed wall and looked at all these results. We saw that all of them are behaving like 3D wall jet. And they're good, but they are comparable with 2D wall jet. It's okay, they are a bit divergent, but still they are comparable. Then we measured the CD, coefficient of discharge, coefficient of drag, and shear length. Then moving on to the velocity profiles within the wall units. That means what we are looking for is how accurately we captured the molecular diffusivity. We have been able to capture pretty good far field, or you may say the macro length, beyond Taylor macro length velocity, but at the molecular level, we still need a little more effort, even though it's quite a good measure here, but still. These are the result comparison with respect to Dr. Candice and other similar research laureate who has been working with the simulation. This is the simulation, and this is the real-time data. Again, this is another figure which I won't be dwelling upon. And this is just for your reference how the PIV and LIF together look. So on your left, it is the V velocity, which is V plus V prime. On your right, it is just the V prime, so that you look and really appreciate the vorticities, how they are. One of data played at 1/20th of the sampling speed means it's just this 1 second length of the time, but played for you at reduced by 20. You see the vortex structures is being traveled up, and how the over here, even though you see there's no movement of almost zero velocities, but in the reality, the velocity fluctuations, the advection, they are being traveled, they are being shifting the heat and enhancing the melting rate. What we observed is perfectly again the same thing. Now this results is actually the melting ice melting. So now we see that they are a bit different. How? Overall, the trend looks pretty good with respect to 3D jet, as we observed with the phase. This is the actual melted ice at different length. And we see that there is a 3D formation from the start. This is the jet start, where the jet is initiated. But as soon as you travel upward, it expands. At a certain length, this is just the curve fitting. I'm not going to go into details of that. They actually might be shifting into 2D. So after looking at the drag coefficient and then looking at the data, comparing it with the 2D and 3D, it was interesting that the jet, actually wall-bounded jet, changed behavior from 3D wall jet to 2D wall jet as soon as it's been introduced in the ice because of the moving boundary. The same thing was observed with the velocity. This curve is for 3D jet, whereas this curve is for 2D wall. That means that at certain length, due to the wall melting, and as we see in the previous slide, that the conical thing is getting flat at the far field, is changing its behavior from 3D jet to 2D jet. It was again, this was a simulation, and we looked upon the simulation, how it actually being implemented, and it totally follows the experimentation. So we still believe that there is probably a transition from 3D to 2D jet in glacial ice melting, and which should be incorporated into the MITGM systems, different models, which obviously will help the scientific study and the proper prediction of melting rates later on. And that's how I conclude my presentation, which totally was on glacial ice melting. I know system showing you different tools of experimentation, showing you how the simulation works. Yes, simulation works, but it has its own limitation. It has a fixed boundary and many other things. That's where you just cannot really use strictly ANSYS or different commercial softwares for moving boundaries problems. The other thing is how the experimentalists are actually validating the simulations to come up with basic fundamental challenging the basic fundamental questions of the different models. If you have any other questions, I'm more than happy to answer. Thank you. Hello. I know everyone is mute, so even if you can just send a question on the chat, I will be happy to answer them.
That's what I had also been waiting. If the participants feel to have any queries, you can ask our trainer through the chat box, or want to say something, please let us know so that we can unmute anyone who's interested in asking any question. So I think people have already gained and they have got to know the technical and the sound knowledge that you have just delivered. And they pretty much, must have gained some valuable techniques and through this session. And once again, I'm truly grateful and thankful to Sir Ahmed joining us and agreeing to deliver the session on such short time span, in spite of all these technical glitches that we had to face today.
Yeah, and I'm sorry as well for being a little bit over the time, and couldn't really see the unforeseen things in Pakistan timely.
Yeah, these are very common and the typical issues that we have to face when you are living in this place.
Yeah.
But nevertheless, everything is a learning day, and definitely we're also learning with all these technical glitches and things to be kept more strict in the longer run in the next series of webinars. Thank you, sir, once again. If anybody is interested having the slides and to review the slides material of our resource person, please let us know. We'll be there to facilitate you, and we have already floated the evaluation form on the chat box. Before you people sign off, do fill this evaluation form and submit it in order to receive the training certificate. And sir, thank you so much. We'll definitely be, taking you, inshallah, in the upcoming months as well for more, technical topics that you're already learning in Atlanta, and that's already a pride for NESPARC as well. People going out on study leave, and they are having their, more technical, and they're gaining and adding more knowledge to their degrees, and definitely to the company as well. And anything, sir, you want to say, and then we'll definitely will.
No, I would be just the last comment will be yes. I have already shared my email address on the chat, so if anyone wants to ask any question or
yeah, sure,
shy enough to ask in public or want to say anything or any comment or any criticize, I'm more than willing to listen to them. The last thing I would say is that yes, I have been working in NESPARC, and it was quite a good experience. But at the same time, it's also true that sometimes NESPARC make you monotonous, make you stagnant. Please try to keep up yourself with the new technologies. Try to keep up yourself with the new challenges. If you're not challenging yourself, that means you're not utilizing yourself. So that would be the last thing I would like to say and mention. That's what I felt for the 6 years in NESPARC.
That's very well conveyed to by you, sir, and to our participants. And now we have to sign off, sir. So thank you so much once again. Take best care. It was a pleasure having you here. Thank you, sir. Thank you.
Thank you so much.
Assalamu alaikum.
Thank you.